let's talk row operations for a bit. So again, row operations are the bread and butter skill of the course. And the more that you can cultivate an autopilot mentality about row operations, the easier linear algebra is going to be for you. That's not going to happen overnight. It's not going to happen in today's class. It might not happen by the end of the week, because we only have one more class before the end of the week. But the more practice, the better with this, because it is a technique, it's a craft, and the more work you have on it, the easier it gets. So it usually begins, as most linear algebra stories do, with a linear system of equations. So here's one on the board. And the question is, let's solve it. And let's do that in hopefully as efficient a way as possible by using the elementary row operations that are available to us. But the first step, before we do that, I always like to say, all right, where are we starting, and where do we want to end up? Let's begin with the end in mind. Isn't that one of those 7 habits of highly successful people or something like that? It's true in mathematics, too. So we're starting with this system of equations. But let's boil it down to its basics before we get underway. Let's get rid of all the variables and put the focus on the coefficients. So my first equation, 3y minus 2z equals 6. What coefficients do I pull out of that? 0, 3, 2, and 6. So the coefficients of x, y, z, and then the constant. And again, we're sort of going to imagine there to be this Maginot line in between the coefficients on the left and the constant terms on the right that makes this an augmented matrix rather than just a matrix. That distinction will be important beginning in Chapter 2. For now, we don't really care so much about what that means, but it just permits us to keep track of both sides of these equations. The second equation, x plus y minus 2z equals 1. We pull out those coefficients. And finally, the third equation, negative 2x plus 5y plus z equals 12. Okay. So we get this augmented matrix. Ultimately, though, where do we want to end up? We want to end up with a set of equations that tells us what value x has, what value y has, and what value z has. Here's beginning with the end in mind. We ultimately want to have that.
On the top row, would it be negative?
Oh, I missed a negative sign. Thank you. My fault. Yes, that would be unfortunate to miss that. So at the end of this problem, we need to know what are x, y, and z. The individual values of them, not their collective values combined together in the sense of these linear equations. But what would the augmented matrix look like for our ending point here? If we have x, y, and z by themselves, then what are the coefficients on the left side of my augmented matrix going to look like? What's the first equation? If the first equation is just x on the left-hand side, then what are my coefficients? 0 for y, and 0 for z, and for x. Yeah. So whatever I do, whatever strategy that I employ to get to this ending point, my ending point is going to look like, in the first row of my augmented matrix, I better have 1 in the x entry and then 0 and 0 in the y and z. Because that means that I have gotten x by itself in that equation, which is, after all, the point of most algebra problems, right? Get the variable by itself so you can find out what its value is. What about the second equation? If y is by itself, what are the coefficients?
0 for x.
Yeah.
1 for y.
Yes. 0 for z. So the second row has a single 1 and the rest are zeros, and the 1 here is in the y entry. And the last row, where z has been solved for, we get z by itself as entries 0, 0, and 1. So we know we're done, in a sense, with a row reduction problem if we have applied enough operations to get us down to a matrix which looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1, in the case of 3 equations and 3 variables, as we have here. That matrix on the left has a name. So here's some terminology coming at you already. For reasons that we'll appreciate more in Chapter 2, this matrix on the left is called an identity matrix. So any identity matrix is one that is made up of just ones and zeros, and in this particular arrangement. It's a square matrix, so it has as many rows as it has columns. And the entries on the, here's some more terminology, the main diagonal, so just to highlight that, the entries on this main diagonal are ones, and the entries off the diagonal are zeros. That should be 2 words. Kind of looks like one. There. Okay, so that's how you recognize an identity matrix, right? Ones on the diagonal and zeros everywhere else. And so if we can manage to employ enough row operations to turn the matrix on top into the matrix on the bottom, then we've solved this linear system. And the values for x, y, and z will be what lies on the right-hand side of this vertical line. Okay? Because then we can unpack this to say, for instance, if we find out that x equals 6, then it would look something like that. Okay. But here's the dirty secret about row reduction, is we don't really need to go all the way that far just to solve. If all we care about is solving for x, y, and z, really it would be enough to find just a single variable by itself that we can then substitute into the equation above it to get the value of that variable, which we can substitute in the equation above it to get the value of that variable, right? That was our end game yesterday. That whether you employed substitution or elimination yesterday, as soon as you found the value of one of your variables, you could then substitute, plug it back in to get the values of the others. And that process of what we call back substitution is also something that we can use in the solutions of these equations. So what that means for us is we don't always have to go all the way this far to find the solutions, if the solutions are all we care about. Really, it should be enough just to get the following. All right. So again, here's my augmented matrix. And as soon as I know the value of one of my variables, that should be good enough. And to find the value of one of my variables, let's say z, maybe just having 0, 0, 1 in that last row is enough, because then I can solve for z. Which then, through a process of back substitution, we could use the equation above it to solve for y. But I can only use the equation above it to solve for y if the equation above it only has a y and a z in it. If it has an x, a y, and a z, then I don't have enough information. So this equation up here should have no x's in it. But then if it has a y and it has a z, then I can use that equation above it to solve for y. So where I'm putting stars here, I'm saying that we should have coefficients there that may or may not be non-zero. In fact, we kind of want the coefficient of y to not be 0, so that there is actually a y in this equation. So let's say that we have 1 right here in the middle. So that at least we have a y in that equation that we can then use the z to solve for the y. And once we know y and we know z, then we can plug those back into our first equation to solve for x, but only if that equation has an x in it. So we need to have an x coefficient that's non-zero. And then the y and the z coefficients can be whatever they need to be. So really, it should be enough for us to get our matrix down into a form that looks like this, where I have ones, or at least things that are non-zero, on the diagonal. But we don't have to eliminate everything that's above the diagonal, because we can just use back substitution to use those equations to figure out the values for x and y, once we know the value for z. So that's kind of relaxing. It's moving our goalpost a little closer to us. So we don't have to do quite as many steps to get to the solution. And this form of a matrix, here comes some more terminology. It's not an identity matrix anymore because it doesn't have enough zeros. But it is what we call a triangular matrix, and specifically an upper triangular matrix. And it's upper triangular because all of the entries beneath the main diagonal are 0. And the entries above the main diagonal may not be 0. They might be 0, but they don't have to be. So it should be enough to get our matrix into upper triangular form. But there's 2 more pieces of terminology I want to point out about this before we go on to actually looking at the steps, because Lay uses these words right away in section 2, and I can see how that might be a little daunting. So what is it that makes the upper triangular form so pleasant? What makes it so pleasant is the fact that in that last row, we have a lot of zeros in the beginning, if we proceed from left to right in this matrix, until we get to that 1 that's here in this position. Whoops, it's kind of heavy-handed here. Let's dial that back. So once we get to that 1, then that tells us that we can solve for z in that last equation. And likewise, in the second equation, we have zeros at the beginning of the row. And then once we hit something that's non-zero, that's that entry there in the middle, that corresponds to a value of y that we can solve for. And we can only solve for it because we know the value of z that's underneath it. And we only knew the value of z that was underneath it because there was no y component underneath it as well. So that makes that 1 in the middle there special. Right? Circle it. It's in a very nice, it's well positioned, let's say, to be able to solve for y. And then likewise with this 1 on the diagonal in the upper right, that we can solve for x once we know y and z, but only because underneath that 1, the rest of those coefficients are 0, meaning that x doesn't belong to the second equation or the third equation anymore. So any entry in our matrix that has a position like this, so the two things we require are that we have all zeros to the left of that position, and so having all zeros to the left means that we don't have the variables, like in the second equation we don't have an x in it. The third equation we don't have an x or a y in it. But then the second requirement is that we all have zeros below as well. So all three of the circled entries in that matrix satisfy both of these criteria. There are only zeros to the left, and there are only zeros below. And any entry in our reduced matrix that satisfies that is called, here's a big vocab word, it's called a pivot position. So a pivot in a matrix is an entry that only has zeros to its left, and it only has zeros underneath. And pivot positions are nice, because every pivot corresponds to a variable we can solve for. A variable we can solve for, or if you like, it's a variable that we can isolate. I'm not sure if this terminology has appeared in the book yet, but we call those variables bound variables, because their value is bound up by the values of the other variables. If we know the values of the other variables, we can determine the values of a bound variable. So that's a lot of terminology, but hopefully the goal here is clear. What we're doing is we're setting ourselves an endpoint that we can apply row operations, but as soon as we've identified the pivot positions, by the way, that's one thing I forgot to mention, pivots themselves have to be non-zero. So the ones we've circled here are all 1s, but really, as long as they're not 0, we should be okay with that. So non-zero entries that have only zeros to the left and only zeros to the below. But once we've found the pivots, we're done with row operations, and we can proceed to then solve for x, y, and z just by a process of back substitution. So our goal in row reduction, always the goal, is to find where the pivots are. And because of the nature of how pivots are defined, there can be a maximum of 1 pivot per row and 1 pivot per column. In each row and column. So for a matrix with 3 rows and 3 columns, what's the maximum number of pivots we can have? We can only have at most 3 pivots in a 3 by 3 matrix, because there's only 3 rows, for instance, and we can only have at most 1 pivot per row. Likewise, it has 3 columns, and so I can only have at most 1 per column. So I can only have at most 3 pivots.
Meaning 3 variables.
3, well, the pivot columns would correspond to variables. The pivot rows correspond to maybe something else. But again, if we think of a pivot as corresponding to a bound variable, that 3 pivots means 3 values that we could potentially solve for. But columns that don't have pivots correspond to variables that we quote-unquote can't solve for. That's a distinction that we'll come to appreciate over the course of hopefully the next couple of classes to figure out what that means. But for now, here's what we know about pivots.